All right. All right. So any questions about anything? Everybody good? All right. So what we're going to do now is talk about a classic sort of data structure, which we're going to call a dictionary or abstract data type. That's what that must be, right? And what is it? We're going to, the input are the red keys, the Ks, and each key is associated with a value, right? And so you can imagine, let's see, we have could be a dictionary, right? You have a word and the definition of the word, right? It could be my social insurance number followed by all the data about me, right? And you can be happy to know that Elon Musk is getting everybody's, if you're Americans, data, so that'll be nice. And so we want to implement these, right? And we can think about various ways of doing it. All right, so the obvious way is you store them in an unordered array, right? Everybody get this? So then we can ask, how hard is it to insert a new, somebody is born, or you come up with a new word, and you need to insert it into the dictionary. Well, it's unsorted, so you just put it at the end of the list, right? So how much time does that take? 1 constant time, right? And then, but now, suppose I'm looking for a particular key. How long does it take? Right? You have to, they're not sorted, so you have to look at the whole list, right? Now you can order them. Well, if you want to order them, right? So now they're ordered. If I want to insert, how long does it take to insert into search? Right? So searching takes log n, right? Using binary search. But if you want to insert somebody, now you got to shift everybody over, right? So now here I'm trying to get him in. He doesn't quite fit. So you got to shift everybody, right? Everybody see this? So clearly these aren't very good implementations. So another option is to have them sorted, but into a linked list, right? What's the advantage of a linked list? Is you can insert people really easily, right? But how do you do a search now? Right? Right? So if you already know the spot, you can insert fast, right? But finding the spot to insert is order n. Yeah? Well, if we're just needing to find it, right? So this search operation is the data structure is there, and you want to find information about Jeff. So it's all the keys are sorted, and you do a binary search, and you find the key Jeff, and you get his information. Does that answer your question? No, not really. All right. Well, what's your question? To do search? An ordered array. Well, so we're not, oh, here's the question. We're not sorting the data. The data is already sorted, right? So this data exists. It's on a computer. It's stored in an array, sorted, right? And now my goal is not to change the data structure, but just to query about Jeff, right? So in this data structure, I do binary search. You know binary search, right? You keep splitting it in half. And then I find Jeff in the data structure. I get Jeff's data, right? And that's the whole operation. I've searched for Jeff. I found Jeff's data, right? Now, this other one is about modifying the data structure, right? So I already have a data structure of size n, and a new person's born, and I want to insert them, right? So I can do binary search to find out where they go, but then I got to move everybody else over, right? Does that make sense? All right, so binary search trees, that's what we're doing now, right? And remember what a binary search tree does is it's kind of like binary search, right? And so it follows one path down the tree, and so the running time is the height of the tree. And it could be really unbalanced, but usually when people say binary search tree, they mean that you have some sort of balancing mechanism so that your tree is balanced. And then you can do, turns out you can insert into the tree and you can search into the tree all in order log n time, right? So that's clearly better than all of these, all right? And then you think, can I do better than this? And it depends on what you define as time and everything, but we're gonna, we haven't, so heaps are good. You can insert in log n time, and but a search still takes order in time. But we often use heaps for things when you want to insert and find the maximum. In fact, what heaps are good is finding the maximum. Yeah. I have it. We'll cover it. This is summary. This is summary. So what a heap is, remember, we might have talked about priority queues, right? What's a priority queue is everything's in a queue except they have priority. And when you say, give me the next, what you return is the object that has the biggest priority, right? So what heaps are good for is priority queues, right? Why? Because you get a new object, you can insert the new object in quick, and you can find the maximum in constant time. And what's a little lie here is you can delete the maximum in log n time, right? So that's all. You know, remember, log is really pretty small. It's almost constant, right? All right, so heaps are good for priority queues. There it is right there. And then hash tables, which we haven't covered either, but you did use some data structure called a hash, which when I saw it on Jackie's form, I must admit I panicked a little bit because I thought hash tables are pretty hard and we're not covering them until much later. But you just use the hash thing, and right. So a hash table we will cover later, and they say you can do everything in constant time, which seems pretty incredible. I might question that, in that suppose I have an array of size n and I want to look up the 8th item, right? How much time does it take me to get the 8th item, right? Well, depends on your model of computation, right? If we're at kind of a value level, I'll let you get the 8th item in constant time, right? But in hardware, it's doing some sort of binary search, right? So you might argue that it takes log n bit operations, but we're not going to go there, right? Everybody see this? All right. And then another thing you might want to be able to do is you might want to go through the objects in order, right? So you want to go through them alphabetically. So a sorted array clearly you just move along, right? A binary search tree, well, sometimes, remember our amortized cost, right? How much does one go to the next guy cost? Well, sometimes it might cost you log n because you have to kind of go somewhere far. But on average, if you go through all of them, right, on average, it'll take you constant time per next, right? And but hash tables, yeah, there's got to be some downfall of hash tables, right? They're not actually stored in any order, and finding the next one is pretty much impossible, right? You just got to brute force it somehow, right? Everybody get that?